Hi, everybody. Good morning, good afternoon, or good night to you all. My name is Hudson Golino, and I'm very excited to have you all here for our course on network psychometrics with exploratory graph analysis in R. And we'll have lots of interesting activities and content in the next 4 days. And I'll take a few minutes of our morning to guide you through how this workshop works and how we're going to move forward. There are lots of novelties in this new iteration of the course that I would like to share with you. We have much more resources that you can use online, including a fresh, brand new website for EGA.net, our main package. A new personal assistant using artificial intelligence called EGA Wizard. I'm going to talk about it later. And several other new stuff that I'm very excited to share with you. Now, let me go here to, to the slides. Okay, so Matt already introduced me. And let me now introduce the workshop and what we'll be going to see in the next 4 days. So the workshop is split by part. Part is just a way to organize the content. There are lots of stuff we're going to cover. And some days we have one part of the workshop in a single day. Sometimes we have 2 or more parts in a single day. It depends on the size of the content and the pace of the interaction between me and you guys. So the first part, we are going to see what is exploratory graph analysis, what it is and how it works. So I'm going to make a very brief introduction to network models. We're going to talk about regularized partial correlations. We're going to talk about triangulated maximally filtered graph, some recent findings from recent simulation studies that we published, and we'll have at the end of the day a guided hands-on activities in R with real and simulated data sets. We are going to also be talking about how to verify the fit of EGA estimated dimensionality structures to the data. And I'm going to focus on one specific fit index that I developed with my team, which is the Total Entropy Fit Index. So to talk about TEFI, we're going to make a very brief introduction to information and quantum information theory and metrics. We're going to talk about channel entropy and von Neumann's entropy, Satoshi Watanabe's total correlation, to introduce the Total Entropy Fit Index, and how we can compare different dimensionality solutions using the Total Entropy Fit Index. Also, I'm going to present some findings from recent simulation studies. And at the end of the day, we have also a guided hands-on activity in R with real and simulated data sets. In the next few days, I'm also going to introduce lots of very useful and interesting techniques. So part 3 will focus on how to estimate the stability of the dimensionality structure, the Bootstrap Exploratory Graph Analysis technique. So how to estimate the typical structure using Boot EGA, how to verify the stability of the dimensionality structure, how to compute the structural consistency metric and the item stability metric. We're going to talk and discuss about sources of structural or item instability, such as wording effects, redundant items, and items that are that don't work really well. I will introduce the idea of configuring variance or structural invariance using EGA, and we'll have also hands-on activities. Part 4 is dedicated to answering the question, how good are my items? And then I'm going to introduce the idea and the concept and the technique of network loadings that are akin to factor loadings. And I'm going to show you how to investigate the metric invariance using the EGA approach. Then we're going in part 5, we're going to talk about our new method that was published last year in Psychological Methods, the hierarchical exploratory graph analysis, which automatically identifies the structure in two different levels, first order factors and second order factors, and how the solution can be different from the regular exploratory graph analysis. The interesting thing is that in our generalized approach for exploratory graph analysis, basically every technique developed can be used in the previous steps. So I'm also going to show you how to do item and dimensionality stability analysis using hierarchical exploratory graph analysis, which is something extremely useful, as you see. Then we will move to more specific techniques and more, let's say, complicated techniques, specifically related to the difference between inter-individual variance and intra-individual variance. So we expanded the exploratory graph analysis, which is a cross-sectional technique, to the intra-individual level. And we developed a technique called dynamic exploratory graph analysis, which can identify the dimensionality structure using network psychometrics for one single individual, for a group of individuals, or for the population, when the data is a multivariate time series or an intensive longitudinal data. In this part, we're going to be talking about dynamical system models. I will introduce to you to the generalized local linear approximation technique, which is the building block of dynamic EGA, and then introduce dynamic EGA in details, how network loadings and network scores for dynamic EGA can be estimated, and also some recent simulations as well as guided hands-on activities. Sorry. And then we have some room for new stuff. In part 7, I am planning to talk about the ergodicity information index and how we can answer the question, okay, if I have intensive longitudinal data or multivariate time series, can I use the population structure to describe all individuals? Meaning, do we have ergodicity in the system of variables? Or by doing so, we lose information, and then we need to have one network structure for each individual in our sample. And I'm going to introduce the ergodicity information index. We might have time for adding 1 or 2 new things. I am planning to talk about unique variable analysis, which is a exploratory graph analysis approach for identifying redundant items. But I need to see if we'll have time for that. If we do, I can add that to the last day of the workshop. This is the web page that we developed for EGANet, our main R package. And here you have information about how to install the package, some workflows, some blog posts about how to use our package, some news, errors, a list of publications, and some teaching materials. So this website is really useful as an additional resource for you guys. Okay, so let's go to the first part of the workshop. We're going to talk about a network approach for dimensionality assessment and reduction, EGA, the introduction to EGA, new fit indices based on information and quantum information theory, and we'll finish the day with a hands-on activity in R. So before we move forward, I need to explain the philosophy behind my teaching strategy. Most, if not all, but most of the quantitative courses are taught in a relatively way that I say that is for people that already know that stuff, right? Is an introduction to that thing for people that already know it. Not here, not me. Not in this workshop. So I don't assume you know anything we'll be talking about. I don't necessarily think that you should know anything, and every necessary concept or idea will be developed throughout these 4 days together. So the goal here is not to have a technical workshop for people that already know this content, but for anyone. The only thing I really need you to know in advance is the idea of a correlation matrix. If you understand the idea of a correlation matrix or a variance covariance matrix, that's all I need. So the general principles for this workshop is a clear logic to each problem and topic. So we will be always discussing why is the topic relevant, how can the research problem be addressed, compelling visualizations, that's the cornerstone of this workshop and my teaching style. We are very much better at detecting visual patterns than understanding written texts or verbal descriptions. And I will use it as much as I can. So every single concept will be explained using visualizations because it's easier for us to understand visualizations and also is more aesthetically pleasant. And also the third concept that I use a lot is the idea of scaffolding to help the development of mathematical, computational, and statistical intuition. Even if you already have a very good, well-developed mathematical, computational, and statistical intuition, my goal is to help you a little bit if you're navigating to a new area or a new field. So I do that by transforming complex processes into smaller steps and by presenting only the necessary mathematical details of these techniques. Okay, so let's start with this intuition development by playing a game. I call this the correlation game. So you have here in front of you 3 correlation matrices visualized as a heat map. Let's start with the correlation matrix to your left. How many factors do you think there is underneath or embedded in this correlation matrix? Can you guess?
Well, are these zero order correlations? Because I guess it's just a bunch.
Yeah, it's just zero order correlations. Yes, just traditional Pearson correlations.
So probably as many as you can establish because the correlations look quite similar and on a range. Yeah. So, well, I'm talking about specifically the third one.
No, the first one. Talking about the first one. We're going to move towards the right. So this is the first correlation matrix.
Okay.
Leftmost correlation matrix. Very difficult to see, right?
Yeah.
Although we have heat map.
Because...
Yeah. It's very difficult.
No. That is the point, that it is very difficult because the correlations look quite similar. So sometimes you can just impose, especially if you use CFA, you can impose as many factors as you want with this type of correlations.
It's very difficult to see. There is very difficult to see. So let's move to the correlation in the middle of the screen. How many factors do you think can be there? A little bit easier, right, than the first one. So just guess. It's a guessing game anyways. Maybe we have one here. Maybe there's another one here, another one here, maybe 4, because the correlations here is stronger than here. So in the diagonal, right? Then compared to the off diagonal. Yeah. But let's move to the third one. So the third one is a little bit easier. How many factors do you believe are there?
2, probably 3, but 2. most likely.
Yeah, yeah, we have one big one here. We can see that's a little bit more blue. The blue here is a little bit more evident than here, and here as well. So maybe 2, but a little bit difficult to say, right? What about now? How many factors is in the left one? And in the middle one, and in the right one. Now it's easier, right?
3, 4.
Yeah, we would say 3 here, 4 here, and 2 here. So what's the difference between the first set of correlation matrices and the second set? Visually speaking, just visually speaking, when we do this.
Some correlations look lower.
Yeah, but in terms of the color pattern that we're seeing, it's easier to see different color patterns or more difficult to see? It is usually easier, right? So here we can more clearly see 1, 2, 3 groups. Here clearly 1, 2, 3, 4, and 1, 2 in the right. So what's the difference between the first set of correlation matrices and the second set of correlation matrices? Yes, exactly. So highlighting darker on the correlations, yeah. The difference is that here we have zero order correlations. Here we have partial correlations, regularized partial correlations, and here we have networks. So how many factors do you think is in the first network here? Just by looking at the network.
3.
3. In the middle? Clearly 4. And in the right one?
2.
Clearly 2, right? So we went from a very complex and complicated problem, just looking at the zero order traditional person correlation matrix. We improved a little bit when we had these partial correlations, but then when we go to the network structure, is much easier, right? To see, is much easier to visualize these factors. So understanding how multiple variables are structurally organized is an important endeavor in psychology and many scientific fields. And as you all know, dimensionality assessment and reduction plays an important role. We have a very, very long history of trying to find underlying structures in multivariate data. We can make a brief historical overview going from the development of the person correlation technique in 1895 to the system of equations, to the beginning of factor models, and also in other fields like in particle physics and information theory. We have the search for a structure or structural organization in quantum mechanics. We have lots of interesting stuff developed in the field of information theory, and also in the intersection of information theory with statistics. It's usually overlooked by psychometrics. So there is at least 2 or 3 different parallel developments in the field, one of which is traditional psychometrics with factor analysis, but also using other type of information, not just the linear relationship between variables that was the basis for factor analysis. So Faye raised his hand. Yes, Faye?
Hi, can you hear me?
Yes.
I have a basic question.
Sure.
Could you tell me how you would define what a factor is?
Yes, good question, and very complicated one. So the definition of a factor depends basically on the model that you're using. So the technical response depends on the model you're using. The philosophical answer is also kind of relatively depends on the technique you're using, but the common ground is a collection of variables that present similar statistical behavior, basically. So we can say, using a factor analysis language or lingual, that they share variance. We can use information theory. We can say that their interaction reduces the uncertainty of the system of variables. We can think from a latent variable model perspective, that there is something common to these variables that are causing their systematic variance. So it really depends. What is common across these three different interpretations is that there is something embedded in the data that makes variables behave more similarly between each other compared to other variables in the system of variables. It can be, they can have higher correlation, they can have higher covariance, right? Correlation is just a standardized version of covariance. They can have higher mutual information if you're using the information theory perspective. But basically, this is the idea. So independent of the, or respective of the technique you're using, when we talk about factors, or when we talk about community of variables, we're talking about things that are coming together like this. And exactly what is your theoretical interpretation for them will differ. And we'll talk about that in a minute.
Thank you.
But great question. So in our workshop, we're going to blend three different areas. We're going to blend network science with psychometrics and information theory. The intersection of the three is what we call the exploratory graph analysis approach, and that's what we are going to learn. So let's talk about the development of networks in psychology. And when I say networks, I'm specifically making a reference to networks that are estimated, not networks that are observed. So there is a long tradition of social network analysis in psychology, and basically this branch of network science applied to psychology is interested in observable things. So for example, you see how individuals are communicating with each other, how people are friends with each other, and then you have links. The links are known stuff. So for example, if I have a Facebook account and I'm friends with Stefano, this is observable. We're friends there, so we have a social connection there. So there is a link between the two nodes, me and Stefano's. So that's observable. That's basically the building block of social network analysis. When I'm talking about networks in psychology, I'm looking at a different branch of network science, the branch of networks that are estimated. So you don't see anything. There is nothing that's observable, like in social network analysis, but you need to estimate the connections between the nodes. So just to make sure that we're framing this in a correct way. So I believe that every quantitative methodologist must also be a kind of historian too, or a detective. So let's make the history. So let's make a summary of the recent developments in the field. So in 2016, Professor Han van der Maas from the University of Amsterdam published a very interesting paper called A Dynamical Model of General Intelligence, the Positive Manifold of Intelligence by Mutualism. In this paper, van der Maas and his colleagues, they proposed the idea of the mutualism model of intelligence as a distinct approach for understanding intelligence, making a distinction between latent variable models in which you have something unobservable, the latent trait that causes the observed variability in the items. And in this paper, they defend an idea that comes from ecology. In a ecological system, you don't have necessarily something unobserved that's causing the variation in the biological entities that you're studying, but every single biological entity impacts one another. And that's the idea of mutualism. And this impact generates or promotes the emergency of something greater than the elements of the system. And that's the basic idea of the mutualism. And then a few years later, Angelique Kramer and Danny Borsboom and Vandermaas and Lawrence Waldorf, also from the University of Amsterdam, published a very interesting paper about comorbidity in psychopathology. And they proposed the idea that we should look at psychopathology not from a latent variable lens perspective, the medical model, what they call the medical model. What's the medical model is basically you have symptoms, and these symptoms, they only exist because there is a disease that causes them, right? So if I have running nose, if I have headache, if my energy is low, and if I'm coughing and I have a fever, these individual symptoms are caused by something else. What's causing these symptoms is an infection, is, for example, flu. And flu, when you remove flu, the symptoms go away, right? So there is a causal connection between something, the flu, causing these symptoms. This is the medical model, or what they call the medical model, or the latent variable model perspective of psychopathology. And in this paper, they proposed something different. They proposed to look at psychopathology not from this medical perspective, but from a perspective in which the symptoms are part of a dynamical system that mutually interacts with one another, causing what we call psychopathology disorders. But they did it from a theoretical perspective. They started a debate in a theoretical way. Then what they did in the same period was they took the symptoms that were described in DSM-5 and they modeled these symptoms as a network, and they discovered and described lots of very interesting patterns published in this paper, The Small World of Psychopathology. So again, they moved a little bit from a theoretical perspective only to modeling as a network the collection of psychopathology symptoms, and they discovered interesting properties that matched epidemiological data. It was a little bit later, at around 2012, that what ignited the field of psychopathology and psychology and intelligence as a call for looking at psychopathology as a network from a theoretical lens, theoretical debate, moved into a technical one. So in 2012, they published a paper, also led by Angelique Kramer, on personality as networks in search of equilibrium. And then they started to implement network models to analyze psychology data. And they developed this package, the QGraph package. And after the publication of the QGraph package, really things exploded in terms of usage and popularity. So the historical overview I'm making here is to conceptually explain that the field of network psychometrics originated from a theoretical debate about how to look at psychopathology as networks of interacting symptoms purely theoretical one, and it migrated towards technical applications of network science and the development of new packages and new methods with the publication of the QGraph package in 2012. And eventually in 2012, oops, sorry guys, we discovered that we had a new field of psychometrics. Using network science methods and psychology data gave rise to new techniques that were very interesting and that could provide lots of interesting information. So let's stop this historical overview here for a minute and let's do a second guessing game. And I have here in front of you a diagram, and I would like you to try to guess who published this diagram. Was it Thurstone in 1921? Was it Danny Boersma and his colleagues in 2012? Was it Raymond Cattell in 1965, or it was Louis Gutmann in 1953? Can you guess? So we have one vote for Louis Gutmann. Faye is guessing Cattell. Another vote for Cattell. Another vote for Gutmann. Another vote for Cattell. A vote for Thurston. Nobody thinks it's Danny Boersman's group. I'm surprised. Yeah, so the correct response is Raymond Cattell in 1965. So Cattell argued for a reticular or a network or a directed graph structure for latent variables in 1965. This model includes all possible reciprocal regression relations between variables and first-order factors. So in 1965, Cattell believed that the best way to model data in psychology from a latent variable modeling perspective was a mutually reinforcing graphical structure. So the Cattell's reticular structure presages the modern network or graph models. And in 1978, Jack McArdle proposed the reticular actual model, the RAM model for structural equation modeling. And Steve Boker, my colleague here at UVA, wrote a very interesting chapter about this a few years ago. And he wrote, Jack McArdle said that one could think of the matrices in structural equation modeling as starting with 0 in every cell and add each regression coefficient or variance covariance from a theory into the matrices. That's the basic idea behind structural equation modeling. However, one could also consider the matrices as starting as entirely filled and then zero out the regression coefficients and variance covariances that should not appear in the diagram. So let's go back here a little bit to the first guessing game. So basically what Jack McArdle was thinking about in terms of structural equation modeling in 1978 was to go from here to here and not going from zeros and then you add coefficients in the matrix based on your theory, which is the usual approach in structural equation modeling. So this was quite remarkable, but the problem is that we didn't have the mathematical tools or the computational tools to do that in the 70s. So Steve Boker continues the reticular in the RAM model, emphasized the fact that structural equation modeling needs to be understood as being a network model. So when Cattell in 1965 proposed the idea of any observational model being embedded in a larger networks of unobserved relations, few understood the wider implications. One of McCardle's main advances was to instantiate this idea of a general network model in a way that could be estimated using cost function minimization optimizers. And that's the tricky part, is the cost function minimization optimizers that was lacking in the 70s, and that it took several years to be developed by the machine learning literature. But we can go back a little bit in time. In 1953, Louis Gutmann published his image theory analysis. And basically what he proposed was to decompose the covariance matrix into the covariance of anti-images and the covariance of images. And it was basically a very similar idea to the estimation of a network using regression methods nowadays, and thinking about the anti-images as the residual of a network estimated using multiple regression, basically. So there is lots of historical precedent to network psychometrics, but they were always mostly theoretical or possibilities, never really implemented. And although Louis Gutmann developed image theory analysis in 1953, he never thought of image theory analysis as being a network, never draw a network diagram, and basically the field forgot about his image theory analysis. And also the idea of the reticular or the graph model that Cattell imagined and proposed in 1965 was never really implemented, because we moved to another direction, the direction of populating the zeros in the correlation matrix with coefficients that are estimated using a structural question modeling. So there's lots of precedent in the history of psychometrics, but things really catch it on with the proposition of the mutualism model of intelligence, the network view of psychopathology from a theoretical perspective, and the development of the first packages in R to implement network methods for psychology data. And that leads us to the beginning of the field of exploratory graph analysis. So in 2012, I was in Amsterdam for a conference, and I met with Dan Borslow, and I was finishing my master's degree, and I was working with measurement theory. So measurement theory and machine learning were two of my big passions at the time. And I wanted to study at the PhD level with Dan Borslow. I went there and I talked to him, and he basically said, I'm not interested in measurement theory anymore. We have a new project going on that we are very excited about. And why don't you go see my students present the next morning? So I went there, and there was 3 people presenting: Angelique Kramer, Laura Brigman, and Sasha Epskamp, 3 PhD students at the time. And when I watched the presentation of the 3, I was completely blown away. I was really impressed with the possibilities. And I invited Sasha to go to Brazil and give a week-long workshop on network methods. And when we were working together, every time I analyzed data that I was collecting back in the day, I could see in the network structure that items would cluster together, they would group together according to my theoretical expectations. Sorry. And what happened was that I started to think maybe we can do dimensionality reduction and dimensionality analysis using network models. But I was very busy with my other projects at the time, so I kept this idea on the side. So later, a few years later, I had time to work on additional projects, and I decided to test this idea. So my idea was, we have parallel analysis. Parallel analysis is the state-of-the-art method for dimensionality analysis, right? It's the first step that most psychometricians and users do before doing exploratory graph analysis. Is the way in simulation studies that present a higher accuracy in recovering the number of true simulated factors. So maybe using network models will be less accurate than parallel analysis, but if it's closer in terms of accuracy, that's enough for a computational proof of concept. So I implemented a big simulation study, and I used network models to do that together with community detection algorithms. And when the simulation finished, I couldn't believe the result. So I redid the simulation again 3 times, and we sat down, we wrote a paper very quickly, Sasha and I said, we need a name for that because people are not going to say, let's use network methods in psychology as a dimensionality reduction technique. And I said, everybody knows exploratory graph analysis, exploratory factor analysis. We're not using factor models, we're using graph models. So let's, as a joke, I coined the term exploratory graph analysis, and it catched on. A few years later, already working here at the University of Virginia, I hired a postdoctoral researcher, Dr. Luis Garrido, that finished his PhD in Spain, working with Francisco Abad at the Universidad Autónoma de Madrid. And he's an expert in parallel analysis. And I said, let's do a work that is basically you against me. So we are going to simulate data, and we're going to stress test EGA against parallel analysis, and let's run a huge simulation study. And he was totally convinced that it was never going to work, that parallel analysis could not be surpassed in terms of accuracy. And we did this stress test, and it generated the psychological methods paper that we published in 2020, investigating the performance of exploratory graph analysis with different types of parallel analysis techniques, something we didn't do in 2017. So that's the beginning of exploratory graph analysis. And what basically we discovered in this 2020 paper doing the stress test was that not just we replicated the original results from 2017, but we saw that actually exploratory graph analysis had an overall accuracy that was higher than parallel analysis with PCA, which is the John Horn's parallel analysis from 1965, but also higher than parallel analysis with principal X factoring, the modification proposed by Humphreys and Egan in 1969. We also discovered that in some conditions that are very important, EGA had a higher accuracy than parallel analysis. For example, when we had a high interfactor correlation and a very small loading per item. And this is a condition that impacts the accuracy of parallel analysis, but not so much for exploratory graph analysis when the data is dichotomous, just to make one example. Okay, so what is it that, what makes exploratory graph analysis work? So let me introduce to you the idea of the Gaussian graphical model. So very different from structural equation modeling. In network psychometrics, the main model used in network psychometrics is called the Gaussian graphical model. And the reason is because that's the model that Sasha started using in his PhD work and implemented in his QGraph package. And is a very good model, very fast, and let's see how it works. So it uses the inverse of the variance covariance matrix as opposed to traditional factor analysis and structural equation modeling that uses the variance covariance matrix to begin with. The partial correlation matrix is regularized using a variant of the least absolute shrinkage and selection operator, the lasso operator, termed graphical lasso, with the optimum level of sparsity selected using ABIC, the Extended Bayesian Information Criteria. So what happens is that we take the inverse of the variance covariance matrix, which is gives rise to the partial correlations matrix. So to step a little bit back, what is a partial correlation matrix compared to a correlation matrix or a zero-order correlation? So in a zero-order correlation, we're computing the linear relationship between pairs of variables. When we have a partial correlation matrix, what we have is the linear association between variables controlling for the effect of all other variables in our system of variables or in the data set. So that's the difference between a zero-order correlation, traditional correlation, and a partial correlation matrix. So when we have the partial correlation matrix, what we can do is we can shrink the values of the partial correlation coefficients toward zero, and we estimate the partial correlations, and then we can visualize these partial correlations as a network in which the nodes represent the variables and the edges or the links, they represent the estimated linear association between the variables. In this case here, the linear association is a partial correlation. When you visualize this partial correlation matrix as a network, and you use, we can use a algorithm to place the nodes in the two-dimensional space. Usually we use the Fruchtman-Heingold algorithm. And what this algorithm does is it places variables with the highest association measures closer in the two-dimensional space, right? So for example, let's take here variables 5, 6, 7, and 8. Their correlations, their partial correlations are stronger, therefore they're closer in the two-dimensional space compared to variables 9 and 12, for example, that are further apart from them because their partial correlations are lower than the partial correlations of variables 5, 6, 7, and 8. So the thickness of the edge here represents the magnitude of the partial correlation. So higher partial correlations will generate edges that are thicker. So basically that's it. And then when we have this network structure, we can compute the extended Bayesian information criteria, which is a fit metric. We can then vary lambda, and as we increase lambda, we shrink the partial correlation coefficients down towards zero. And when we do that, we can compute the extended Bayesian information criteria one more time. We can keep increasing lambda, which means we're shrinking the partial correlations towards zero, and we can recompute the extended Bayesian information criteria index again. And we can keep doing that. And now what we have is we have a search. So we start with a highly interconnected network of partial correlations like this here in the top left. And as we move along the search for different values of lambda, we are shrinking the partial correlations down towards zero, and we record the extended Bayesian information criteria. If we do a search of 100 different values for lambda or 100 different levels of sparsity of my network, I can try to find exactly the value of lambda or the exactly level of sparsity that minimizes this information criteria, the extended Bayesian information criteria. And that's my final network structure that gives rise to the Gaussian graphical model, which is basically a network. The estimation method is a network estimated using regularized partial correlations in which the level of sparsity is defined by the value of lambda that minimizes this fit index, the extended Bayesian information criteria. So when we do 100 different searches, we find that this network here in the top right is the one presenting the lowest extended Bayesian information criteria, therefore is our final estimated network. So we go from a correlation matrix or a variance covariance matrix to a partial correlation matrix, fully connected, and then we shrink the values towards 0, and then we compute this fit index, and we see which level of sparsity is minimizing this fit index. So let's see one example here. So we have here in the left, we have the zero order correlations. In the right, we have the resulting regularized partial correlations estimated using the ABIC-GLASO approach that I just showed. And in the extreme right of the screen, you can find the resulting network structure. So when the interfactor correlations is 0, what happens is that within the factors, we have correlation values that are above 0, right? So you can see here that in the off diagonal of the correlation matrix, everything is 0, but in the diagonal, we have values greater than 0 because when we simulated the data, we constrained the factor structure in a way that the factors are unrelated to each other. So they don't communicate. There is nothing shared. There is no variance shared. So the resulting estimated correlation matrix is a matrix like this. When we estimate the regularized partial correlations for the same data set generated using the same approach, we can see that the value shrinks towards 0, so they're smaller. And in both cases, they're easy to see. And when we estimated the network, we can clearly see that the network is a set of unconnected clusters. So we have 3 clusters here that are emerging, and they're unconnected. When there is correlation between factors and we simulate data, we can see here in the left that it's a little bit difficult to see the number of factors underlying this correlation matrix, but it's very easy to see when we apply the regularized partial correlations, right? We have clearly 3 sets of higher regularized partial correlations in the diagonal compared to the off-diagonal values. The resulting network plot looks like this in the right. We have 3 clusters of variables, 3 clusters of items. They are interconnected, so there is edges between clusters as opposed to this completely isolated set of clusters here when the factor correlation is 0. But if you look at the network structure, you can see that within cluster, the regularized partial correlations are higher than between clusters. As we increase the interfactor correlation and we have a very high interfactor correlation, it's basically impossible to see the number of factors here in the correlation matrix, much easier to see when we have the regularized partial correlation matrix. And again, when we have the resulting network structure here in the right, we can see clearly the 3 clusters. And again, we have edges coming from one cluster to another one, because we have correlations between factors in the data simulation mechanism. And again, the interfactor regularized partial correlations are higher than between factor regularized partial correlations. And that's basically why exploratory graph analysis with ABIC-GLASO works so well. It helps to clean out residual values that are not due to the factor structure itself. And that's why exploratory graph analysis with the Gaussian graphical model presented a higher accuracy than parallel analysis. So let me see here a question in this chat. Sorry, it's probably obvious, but I missed the why the partial correlation matrix used instead of the correlation matrix. Because exactly because of this. Because if you use the factor correlation, you have information that's not related to the factors that are still present. So you will decrease the accuracy of finding a factor. Just look at the heat maps in the left, especially the last one here in the bottom. Just by looking at this heat map, so this is a correlation matrix plotted as a heat map. It's very difficult to visually see the number, how the variables are clustering, right? But when you clean the structure, so when you shrink the correlations towards zero using regularized partial correlations. What happens is the variables that belongs to the same factor, their regularized partial correlations are much higher than the factors that do not belong to the same factor, right? So the values of the regularized partial correlations are much higher in the diagonal of the matrix compared to the off diagonal of the matrix. And that's what drives the higher accuracy of exploratory graph analysis, because it's using regularized partial correlations. Another good questions, I may be missing something, but why are the diagonal elements of the partial correlation matrix 0, not 1? I thought they are the partial correlation of each item with itself. Yeah, so when we're it's just a matter of plotting. In the code, we put back ones in the diagonal. But for visualizing the network, what one would be is a self loop in the node, and we don't want to reflect that because that would be confusing. So the resulting network is this here in the right.